It's my pleasure to welcome you all here today to the inaugural Professor A.K. Saha Memorial Lecture, an event we organize on behalf of the Geological Institute, Department of Geology, to commemorate the birth centenary of our revered teacher, Professor Ajit Kumar Saha. I request all dignitaries to please take your seats for us to start the program. Kindly keep your mobile phones in silent. Thank you. Now, I would like to invite the President of the Institute and our Head of the Department, Professor Saibal Gupta, to address the gathering.
Distinguished guests, alumni, well-wishers, and students of Presidency and neighboring institutes, I wish a very good afternoon to all. I welcome you in this August gathering, which is named as the Professor A.K. Saha Memorial Lecture. This is a part of our year-long activities we have planned to celebrate the birth centenary of the legendary teacher of this institute. He has left indelible marks through his teaching and research, which are still very much relevant even after 3 decades since their death. On this occasion, let me share a few important facts about the event. On 25th May 2024, the A.K. Saha Memorial Committee was formed in a meeting in the department, which was graced by the presence of our distinguished alumni. On 12th November, the inaugural edition of the Geological Institute Conference, GIC, took place. Students, research scholars, and postdoctoral fellows from different parts of the country participated in this one-day national conference, with a total of 45 oral presentations and 40 poster presentations. On 21st and 22nd March, we had our 2-day national seminar named Dynamic Processes of the Earth, from Deep Interior to Surface. This engaging event spread across 4 sessions, featured a rich exchange of ideas through 44 oral and 59 poster presentations, from faculty, postdoctoral fellows, research scholars, and students both from India and abroad. The 64th edition of annual magazine of the Geological Institute, Govinda, was dedicated to Professor A.K. Saha at the annual general meeting in December 2024. Furthermore, we have successfully established and mobilized the Professor A.K. Saha Memorial Fund, which stands as a powerful symbol of our collective commitment to furthering his vision. We extend our heartfelt thanks to Dr. A.K. Saha's family and our esteemed alumni for their generous contributions, which have brought the fund total approximately Rs 9 lakhs. A large part of it will be used for incentives and travel support for students and research scholars of the department. Today, on this auspicious day, we gather for the Birth Centennial Lectures, the Professor A.K. Saha Memorial Lecture. Though initially we thought to hold this on his birthday, through 25th of May, we had to reschedule it today for the ensuing semester examinations, which begins on 22nd of May. We plan to continue this lecture every year as we do for the case of Professor A. Saha Memorial Lecture. Once again, I welcome and thank you all for being here with us. Thank you.
Thank you, sir. Now I would like to call on stage Professor Saibal Gupta, our speaker for today, and the head of the department, Professor Shankar Bose, to offer floral tribute to Professor Shah. Thank you, Professor Bose. I would now introduce today's speaker, Professor Saibal Gupta, to the audience. Professor Gupta is at present an HAG professor in the Department of Geology and Geophysics, Indian Institute of Technology, Kharagpur. He currently also holds the responsibilities of the Associate Dean, Faculty of Sciences at IIT Kharagpur. Professor Gupta earned his bachelor's degree in geology honors from Presidency College, University of Calcutta in 1987. He completed his master's degree from Calcutta University in 1989. Although examinations for the masters in that year were held in May 1990. Subsequently, he spent a year as a CSIR Junior Research Fellow at the University of Calcutta. In October 1991, he left for the United Kingdom with a Cambridge Nehru Fellowship and completed his PhD from Department of Earth Sciences, University of Cambridge, UK in 1995. Returning to India, he joined as a visiting lecturer in the Department of Geology and Geophysics at IIT Kharagpur in August 1995. He has worked at IIT Kharagpur all his professional life, from an assistant professor in 1998, associate professor in 2004, and then professor in 2010. Professor Gupta's research interests include nature and evolution of orogeny with a particular focus on the thermal evolution and composition of the lower crust. He integrates structural, metamorphic, geochemical, and geophysical methods to study crustal behavior during orogeny and its exhumation. His work extends to terrain amalgamation and the construction of supercontinents such as Rodinia and Gondwanaland. He also applies his expertise to geohazard assessment, mineral exploration, and the tectonic control of arsenic contamination in groundwater. His interests also reach beyond Earth through collaborative efforts with the Space Application Center in Ahmedabad, where he investigates terrestrial analogs for Martian surface features. He has published 75 research papers across many renowned peer-reviewed national and international journals like in Journal of Structural Geology, Tectonophysics, Journal of Metamorphic Geology, Journal of Geophysical Research, Planets, Journal of Geophysical Research, Solid Earth, Geophysics, Scientific Reports, Natural Hazards, Precambrian Research, Journal of Earth System Science, Icarus, and many more. He has supervised 17 PhD students, many of whom are now researchers in national and international organizations, universities, and institutes. Today, he will be speaking on continents, water, life, on Earth and beyond, the geologist's story. Please join me in giving a warm welcome to Professor Saibal Gupta.
I can be heard, I think. So as they are setting this up, just it gives me an opportunity to say a few words, which is what I intended to say preceding my talk. It's a great nostalgic feeling for me to be back here. And this particular hall, I remember it more for watching Kurosawa and Satyajit Ray retrospectives rather than anything else. What is really nice to know now and realize is that people can actually understand words when they are sitting in the audience here. Because when I was a student, the acoustics were extremely bad. And now it's significantly better because I could hear people when I was there. Apart from the nostalgia, the sheer nice feeling of being back here, I must actually thank Professor Shankar Ghosh and the Department of Geology of Presidency University, and of course the Geological Institute, of which I also am a member. So all of this, for making this possible, for me to be able to deliver the first lecture in memory of somebody who I think represented to us at that time the Department of Geology, Presidency University. And it was more or less realized all through the country that this was the case. It is let me just begin from this point. Anyway, I think we're a little overdue. So once again, thank you for having me here to talk on something that is not really related to what I learned when I started off learning here, but it is in a way related, and related to the very gentleman after whom we're all assembled here today. Professor Saha was a person who actually not only did geology, but he also realized the importance of doing geology in such a way that he could reach out to other disciplines, to reach out to the service of mankind. So he actually was always exploring the frontiers of what could be done, and what could be done in this particular country. So as a result, I think the only things that we possibly were able to imbibe in some way, at least I have been able to imbibe in some way, is trying to explore the frontiers of what I could do with whatever little I knew about the subject. And whatever I have done so far, in fact, dealing with planets, which are planets and planetary bodies outside the Earth, is something that I never thought of doing, that never thought that I would be able to do when I started off doing geology. So today, I'll be talking about a few things that I have done together with my students and a very useful and efficient group of collaborators who have taught me a lot over the years. So I'll be talking about continents, water, life. Now, these are three very important ingredients to our existence. We survive as life because we have continents and water. Exactly how this happens, water is fairly obvious. Continents are not that obvious, but we will be going into what exactly it means, and even what the formation of life means. And then, when I end, I hope to tell you how that it makes us realize how lucky we are, really, that we are living on this particular planet, where a number of factors luckily came together to enable us to exist. Now, if we begin right from the start of where it was here, Professor Saha, this is not how I remember him, by the way. I graduated in I joined this department in 1984, and when I joined, he was still head of department. He retired officially the next year, continuing as an emeritus professor, but he was no longer head of department. But one of the things that we realized Professor Saha was very fond of was this thing to the right. So those of you who may not know Professor Saha would actually know this image to the right. And this is one of the areas in which he spent much of his life working in. This is a map of the Shingon pattern, something that he was fascinated with, a fascination which we could understand as students had something to do with examinations which would appear every alternate year. There used to be a question on Shingon every alternate year. And then in that particular context, we were forced to study it, and we didn't like it when we did. And we really wondered, what made Professor Saha so fascinated with Shingon? Well, now, at the very end, let us say, of my own academic life, I now realize that there's a lot going for it. There are reasons why he found this so fascinating. Now, this little bit of Shingon, it's a part of the Indian Earth's continental crust, which is among the oldest bits of the continental crust we know of in India. Not just that, it is also significantly preserving several bits of Earth history which are actually not yet documented elsewhere on Earth. And that really has to do with, let's say, the emergence of continents, something that has been done with Shingon very recently. Now, in this region, if you look at this particular map, you see a lot of rocks actually marked on here. One of the units that is very prominent is this particular one here. This is the one which gave us a lot of, what should I say, a lot of sleepless nights when I was students. This is the Shingon granite. There were apparently 12 phases of it, and 12 types of granite which were erupted in 3 phases. I don't still remember exactly what they were, why they were there. But I do realize now that it actually is a significant component of any part of the Earth's crust that we look at. You have granites of various sorts which actually stabilize the continental crust elsewhere on Earth as well, not just in Chile. So there was a reason why he was interested, because this was one of the earliest parts that you could see. And it was telling us bits about Earth history, which we are not able to really see. We can't go back in time. So all that we can tell about what happened in the past is by looking at these rocks. So what really is fascinating is this is the way in which you can actually begin to work out how continents were formed. And why is that important? Because if you look at any map of the Earth, so you will see that it's a distribution of continents as well as oceans. Now in this, you see that you have the green areas which represent the continents, you have the blue areas which represent the oceans. Now essentially the Earth's surface is dichotomous crust-wise. So we have 2 types of crust. One is the type of crust that dominates what we see in the green areas, the continents, and the other part is the part that lies below the blue waters that we see here, and that is basalt, which makes up most of the oceanic crust. So we have completely different types of crust on Earth, so it's essentially a dichotomy. Now, this dichotomy is not just apparent on a map. There are reasons why they are different, because continents and oceans themselves are fundamentally different entities. Now, if you look at continents, the reason why we realize that they are different from the oceans is, first of all, they're more elevated than the oceans. We have a mean sea level. And above that, right, we have the continents on which we live. So we are able to live on continents and we can look and enjoy the seashore. But then what lies below the sea is also rock, and that rock is very different from the continent on which we live. Now, continents themselves, on an average, have rock division, which is that of a rock called a granodiorite. Now, these are silicic rocks. Now, by silicic, throughout this talk, I'll be referring to those rocks which have a silica weight percent of over 65. So you have more than 65, more than 2/3 of the rock is dominated by silicon dioxide. So continents are largely made up of one type of rock, which is silicic, which is called the granodiorite. On the other hand, if you look at the oceanic crust, it's made up of different rock. This rock is a basalt, and this basalt contains significantly lower quantities of silica than the continents. A basalt contains only about 45 to 55% of silica. Now, we know that continental crust is also less dense than the oceanic crust, and that really is a consequence of the amount of silica it has. Because continental crust contains more silica, and silica is a lighter component, therefore, overall, the basalt, which contains less silica, is heavier. So there is a density contrast between the continental and oceanic crust. Now, in addition to that, we also know that the continents are thicker than the oceans. So the continental crust on an average is about 35 kilometers thick. In places where we have orogenic belts, we have origins in other words. We have a thicker crust, could be as much as 75 to 80 kilometers thick. Now, those regions contrast with the oceans, where most oceanic crust is only about 10 kilometers thick, and less than 10 kilometers thick. Below transform faults, it's barely about 2 to 3 kilometers thick. So, really, there is a drastic difference in the thicknesses of the crust that we see making up the continents and the crust that makes up the oceans. Now, together with that, of course, is an old part that there is a component that I'm not going to be talking about too much today, and that is the age part here. If we look at the continental crust, that is about 4 billion years old. The oldest part of it is about 4 billion years old. Whereas if you look at the oceanic crust is only around, the oldest part of it is only about 200 million years. So there is a drastic difference in ages between the two, and that we know happens to be because of a phenomenon called plate tectonics, which actually consumes oceanic crust repeatedly over time, and it cannot do the same with continental crust. Now, why are these continents so important? Now, in the past, we knew there were continents and there were oceans, but for a long time, we never really realized why they were so important. Now, continents, we realize that sometime in the geologic past has emerged from below sea level to above sea level. And this emergence from below sea level, this has been responsible in a very significant way of controlling the surface temperature of the Earth. Now, the surface temperature of the Earth, it varies from place to place on the surface, but overall it has maintained an average value that can actually sustain liquid water on its surface, and that has happened at least from 4 billion years. As far as the rock records can tell us, we have sedimentary rocks which were deposited underwater from 4 billion years. And that means that we must have had liquid water for 4 billion years, and we still have liquid water on the Earth's surface today. So the surface temperature must have been roughly within that, give or take variations in the atmospheric pressure. Now, the emergence of the continents from the oceans themselves, apart from controlling the surface temperature, acting as a natural thermostat, in other words, it was also responsible for increasing the amount of oxygen that is there in the atmosphere. This was indirect, but nevertheless, this was responsible. The emergence was what was responsible for what followed. The two great oxidation events, one at 2.4 billion years and one at about 800 million years. So both of these are linked to the emergence of continental crust from below the oceans. So the continents are actually very, very significant, not just for maintaining surface temperature, but ultimately, in some ways also, for sustaining life. Now, the question then comes, how do we make continents? If we look at the Earth, right, and try to look at how continents are created, we first have to once again realize what they are. Most continents are made of silica-rich rocks, and these contain over 65% silica. Now that's one of the fundamental things that's of importance in making a continent. Now on rocky planets, those which contain silicate interiors, You have a silicate mantle, which is roughly of the composition of a particular type of meteorite called a chondrite. And this type of rock, right, dominates, this chemical composition dominates the Earth's mantle. And when it melts, the Earth's mantle melts, it produces a liquid which has the composition of a basalt. Now, a basalt has 45 to 55% silica. The mantle has a little less than that, it's around 40%. Now, we normally assume that silicic rocks, which contains more than 65% silica, these are produced by a process called fractional crystallization of a basaltic magma. Now, a basalt liquid is produced by melting the mantle. And what we are doing then is crystallizing things from the basalt magma, which contain less silica than the basalt. As a consequence, the composition of the magma progressively becomes more silica-rich and ultimately becomes silica-rich enough to form and stabilize the continent. Now, to do this, we now realize that a basalt or basaltic magmas cannot fractionate to generate a granite. You need to have a certain amount of water inside that basalt for Bowden's reaction series, as many of us know, to operate. If you don't have water, you cannot actually fractionate a basalt to give a granite. As simple as that. Now, this is therefore one of the best ways to make a granite. But there are other ways, and that is by making other types of rocks. Now, we know there are certain types of rocks which can be partially melted to produce a granite, but we're still not sure exactly what these rocks should be. What type of rocks should it be? Should it be only one type of rock? We now realize there are a number of different varieties of rocks which can actually melt to produce granitic rocks. Now, the precise composition is not determined. So we know that it can vary. It may need not only be one single type of rock, but it has to be something which could be possible in earlier. Now, how did the very first continent form? At that particular time, now, if we want to really examine this, it's important for us to know, because the processes that are responsible for producing continental material today, these may not have operated in the past. So therefore, we need to actually understand, right, how the first little bit of continental crust must have formed on Earth. But the problem is, the Earth's surface is so very dynamic, is that weathering and erosion over ages has really degraded the earliest continental crust. So we can see evidence for it, but we may not actually be seeing the oldest bit of continent that was produced on Earth. So where do we see this? Because on a dynamic planet, it's never going to be possible to see that. So we can actually look for silicic rocks on other planetary bodies, because we know that these other planetary bodies, for example, the Moon, Mars, Venus, these are rocky, and we know that they contain the capability to actually produce silicic rocks. So it's actually important for us to see if we can find any evidence of granites being produced on these planets. Maybe that will be preserved there because that was frozen in time. Now, are there silicic rocks on other planets? Now, if we look at the planets, then it's only the Moon is the only one on which we have physically landed as humans. Mars has had rovers on it. Venus has just had one land mission. But whatever little information we have tells us that planets such as Mars, Venus, and Mercury, the surfaces are dominantly composed of basalts. This much we know. And there are very rare silicic rocks. They're rare because we suspect that there could be a few silicic rocks, but we're not certain. There are reports, but again, unless you can actually have more definitive proof, more convergence of evidence, you can never prove that there were silicic rocks there. So the most accessible rock, if you're going to look outside the Earth, search for silicic rocks, the best place to look at is the place which is most accessible to us outside the Earth, and it has to be the Moon. Now, this idea, not for looking particularly for planets, that man could go to the Moon, first originated, I think, when people have been thinking about it, but somebody to put pen to paper and write about it was really good. And this is from a very old book. This is, I think, the cover of the very first edition that was produced. So we think this idea that it was possible to go to the Moon to actually find things out stems from a lot of things that this person told. Now, what's happened here? But this is worrying. There were two images here. Now, for some reason, those images are not visible. So one is the near side of the moon. I mean, this was the part that we can actually see. One is the far side. I put more images actually missing afterwards, because this is going to be a problem if the images can't be seen. So there is a near side and there is a far side. Now, I just want to mention what this means. It means that when we are looking at the Earth's, at the moon, we are only able to see one face of the moon. Because of the Earth's gravity, the moon's surface is actually tidally locked. And so we can't actually see the whole of the moon. We can only see one side. That side is called the near side. The part that is away from the Earth is always away. We've never actually seen that physically unless we send crafts to the other side to photograph it, as we have. That is called the far side of the moon. So we have two different sides. So we are able to see one side which contains a lot of craters and the other side which is the far side. The moon's surface, however, is not made up of basalts dominantly. It is made up of a rock called an anthracite that actually dominates. It's not the only rock type there, but there are some other types of rocks which make up the surface of the moon. But this is one of the ones that is important. Within some of the craters that you see on the moon, you have patches, dark patches, which you can see on the moon even if you look at it at night. These dark patches are basalts. And these have been erupted into craters that were formed on the moon's surface by meteoritic impact. So, how then do we begin to look for silicic rocks on the moon without getting samples of these rocks? Now, the first thing that we need to worry about is it worth looking for it? Is there any chance that we might find silicic rocks on the moon? Well, one of the advantages we have or the moon has over other planetary bodies is that we have some return samples. And these were primarily from the Apollo missions. So Apollo 11, Apollo 12, Apollo 14, Apollo 15, Apollo 17, all brought back samples. And indeed, all of them brought back samples that had certain traces of the presence of evolved lithologies of silicic rocks. Now, most of these return samples, anyway, the samples that you see of the basalts are either clasts or the breccias. Among the silicic rocks that you can see, you have both crystalline varieties with quartz and feldspar, and you also have glassy material, which tells you that there were silica-rich liquids present. Interestingly, in these rocks, which are mostly granophiles, there are no hydrous minerals at all, no evidence of any water being present inside those primitive networks. There are a few samples, very, very small, in which you actually can see graphitic integrals, granophyric integrals between quartz and K-feldspar. And there is evidence of a phenomenon that you can see in these rocks called silicate liquid immiscibility. It means that when you fractionate a basaltic magma without water, you can actually wander into silica-rich domains where the magma itself splits into two. One composition which is around 50% weight percent silica, and the other part which contains over 90 weight percent. So you can get very silica-rich magmas by this particular phenomenon called silicate liquid immiscibility. And there is some evidence for this in the lunar samples we've seen. But are they silica? These are very small samples. Are they silica-rich constructs on them? Mountains of silica, as we will see on Earth. That's what would really count. And this evidence we have to get from spectroscopy. None of the Apollos have actually landed on a silicic construct. Now, if you look at the surface of the moon, there are red spots there. And these red spots are important because silica-rich rocks have a higher albedo, so the reflectivity is better, the reflectance is better, and these actually have a greater absorption in the ultraviolet range. As a consequence, the red color is what we see. So when you see these red spots on the moon, these are likely to be regions which actually contain higher amounts of silica. Now, also, these red spots seem to correspond to regions that have high concentrations of the element thorium. Now, thorium is an element which is called an incompatible element, an element which becomes concentrated in liquids every time they form. So whenever you melt a rock, some elements actually base elements prefer to go into the liquid itself because they cannot be easily accommodated into the crystalline structure of the minerals present. So, as a consequence, thorium itself, when it's there, it would tend to be present in more evolved lithologies, and that really is what we're seeing coinciding with the hotspots here. And then there is this spectroscopic feature called the Christensen feature, and you actually see this in the emissivity spectrum. Now, the emissivity spectra is a spectrum that is really simply a measure, it's an indicator of
how much silica it has. Its position, the wavelengths that it absorbs, it's actually an indicator. And I'll talk about this a little later, why it actually is important for identifying silica-rich lithologies. It is important primarily because for other minerals, you can actually have other indicators, other bonds, which can tell you which minerals are present. Unfortunately for quartz or feldspar, you do not have specific spectral absorptions which can tell us about their presence. So you have to gauge the presence of silicic rocks from alternative proxies. Now, we have, based on these criteria, 12 documented possible silicic constructs on the moon. Now here, the moon itself, I've stretched it out into 2D. So the sphere, the image that you could not see, right? There were two moon images there. When you stretch it out in 2D, right, you have these 12 constructs. This part, really, is the near side, the part that we can actually see. The parts to the side are the other side of the moon when we've unwrapped it. So these are the far side of the moon. You can see for some reason, 11 of these features are concentrated on the lunar near side. There's only one that has been identified as a possible silicic construct of the lunar far side, that is CBVC. It's called the Compton-Berkovich Organic Complex. Now, among these things, these features that you can see, 2 are marked in yellow. These are marked in yellow because these are the features on which we tried to do some work. LM is called the Lassell Massif, and W is called the Wolf Crater Complex. So I'll be talking now about the Wolf Crater Complex. Now if you take a closer look, this is what the Wolf Crater Complex actually looks like. So this is a crater. Now it's no wonder finding craters on the moon. The moon is extremely cratered because there are meteoritic impacts happening all the time. Now, the question is, you can see craters here, there is another one possibly here, small sizes, some are larger in size. So this is the Wolf Crater itself, and itself, within the Wolf Crater, there are smaller meteoritic impacts also. This is the floor of the crater. These are the rims of the crater, and you have several parts of the crater together that make up this particular complex. Now, this was identified as a possible silicic construct by Greenhagen et al. In 2017. Now, we use a variety of spectroscopic methods to try and find out whether these are silicic lithologies or not. So we use particular instruments on these missions for the morphology, some for the composition, some we use for the gravity data, right? And then for all of these, we have to use certain specific spectral analysis techniques, right? And we use the ones that are defined out here. Now, when we look at the morphology of the Wolf Crater Complex, now I won't go into the technical details of exactly what we did, but when you divide the Wolf Crater into several different parts, just for the purposes of studying the morphology, what you notice is that all of these features, they have astonishing similarities with features that are characteristic of caldera collapse or nothing. So it appears that there were fault-bounded features along which things collapsed in the center. So the crater was it really seems to be created as a caldera rather than a meteoritic impact crater. And not just one, there are several stages of this collapse that we can see. Now, from the sides of the complex that we see, we can see that there are lobate features which are protruding down and solidified. These are most likely to be melts that solidified as they were pouring down. So as they were moving down, because they were so viscous, as a silicic melt is likely to be because it's so polymerized, so they would tend to form lobate flows. Now, the central part, that is this particular region, that is filled with mare basalts. So this part is actually filled with mare basalts. The crater rims themselves are elevated above the rims, above the central part. All these features tell us that this crater, the Wolf Crater Complex, was not created by meteoritic impact. So it must have been created by some alternative technique, and that particular thing is most likely to be a volcano. So it must have been a volcano that erupted and the caldera was created because of the collapse of the central part. So now, if we now try to see the composition of features around the Wolf Crater, you see this is a map of the emissivity spectra, and this is called the Christensen value. Now, the blue parts have low Christensen feature values. Now, the lower the value, the Christensen feature is a feature in the emissivity spectra, which is related to silicon-oxygen bond vibrations. So if there are a lot of silicon oxygen bond vibrations, the larger the amount, the energy associated with these vibrations is very large. As a consequence, what happens is the energy that is actually emitted also happens to be higher from these particular bonds. So areas that contain more silica will actually emit vibrations which are higher energy. If they have higher energy, it means they'll have lower wavelengths. And the Christiansen feature is measured by its wavelength. So if the wavelengths are less than 8, it tells you that these particular features are most likely to be very silica rich. And as you can see, the blue region is all around what we think is the rim of the crater. So that is dominantly composed of rocks, which are likely to have more than 65% silica. And you can see that the floor of the crater is very different. This is the part which we think is Mare basalt. Now, we have other minerals apart from silica-rich things that make it up. And among these are pyroxenes and you have magnesium silica. Now, among the pyroxenes, you have both low calcium pyroxenes, you have high calcium pyroxenes, both forms are present. And these spread across this particular domain of composition space in the pyroxenes. Now, another interesting feature is the presence of this magnesium spinel. Right? It is MgO0.82. This coexists with silica-rich parts. This is very strange because this is a mineral which is very deficient in silica, and yet it is coexisting with silica-rich ones. So how can we actually explain this coexistence? This is what we're seeing on the moon. It's not something that we see on Earth. If you look at the results from the geophysical information we have, that is the gravity data. The gravity data, it's got from the Grail instrument, and there we do the Boger gravity anomaly, the studies, and you can actually see that it indicates that this low density material, silica-rich material, is less dense than material that has lower quantities of silica. So the silica-rich material itself, which is less dense, extends down into the crust up to a depth of at least 30 kilometers. We can tell that for sure. That means the crust below this is 30 kilometers. It's granitic or silicic in composition up to that depth at least. So the rest of it is anorthositic, and you've got basalts around it. Nevertheless, you have parts that are silicic, which actually extend to considerably great depths. Now, what about the age? How old was this silicic magnetism, if we think it is? Now, if we look at the rims of the crater, so RZs are the rims of the crater, and you can get the age. We've not got samples, so it's not an isotopic date. So what you do is to date them based on a technique called the crater size frequency distribution. And when you use that, you get ages which vary from 3.8 to 3.6 billion years. That is the age of the silicic rocks at the rims of the volcano. The central part of the volcano, on the other hand, which is basalt, it just simply got rocks which is 2.6 to just 2 billion years. So these erupted afterwards, after the caldera collapsed in the central part. So if I now take all of these features together, we have features that indicate viscous lava flows, we have caldera collapse structures, there are a few post-caldera domes which are also silicic in nature around it. The compositional constraints like low distance and feature position. We have very low iron oxide abundance. This is important because it overrules one particular theory that we talked about just now. And we have an overall low mafic mineral abundance there. And of course, then we have low gravity signatures up to about 30 kilometers. All these features, if you take them together, these are consistent with the existence of a silicic volcano. So you must have had a silicic volcano 3.6 to 3.8 to 3.6 billion years old on the moon. Today, it exists as a volcanic volcano. Now, how did this silicic volcanism originate? Now, the interesting part here is this existence of the magnesium spinel. Now, magnesium spinel in coexistence with silicic constructs. This is not something that's usual, but we see it in the Wolf Crater complex. And this really suggests that the origin of the silicic magma was most likely by melting of rocks, such that you actually get silicic-rich melts and spinel together. And this can only happen in systems. Those who are familiar with igneous spectrology would recollect a system called the phosphorite anorthite system, the olivine plagioclase system. And that system, in between, there is a field of spinel, Now, whenever spirale crystallizes from a system which contains fosterite and anorthite, then in that case the corresponding melt has to be extremely silica-rich. Now, fosterite and anorthite is an essential component of one major type of lunar rock, and that is called a proctorite. That is very common on the moon, and it exists along with the anorthosites in the highlands on the moon. So, if you have proctorites present anywhere and they melt, you will actually get silica, magnesium silica, and granites together formed at the same location. Now, if one of the alternatives, you could have had silicate liquid immiscibility, fractionating of dry silicic magma into the field of silicate liquid immiscibility, such that you actually separate one part out into a very silica-rich composition, and the other part which is, of intermediate composition. That also seems very unlikely, because in that case, all the mafic minerals that you can actually see around it would be extremely iron-rich, and that is not what we are able to see. And of course, we see these high thorium constraints. This is compatible, it's incompatible with silicate liquid immiscibility, but it's completely consistent, right, with the formation of melting of proctorites. So in other words, lunar silicic magmas, these appear to have formed by crustal melting of pre-existing rocks by basaltic underplating, and these pre-existing crustal rocks are most likely to be of the compositions such as proctorites. Now, if you look at this, though, what triggered this magmatism? When the moon actually formed, we believe there was an early lunar magma ocean, and this crystallized to form a cumulate layer of anorthosite, proctorite, gabbro-norite, all these things, forming the lunar crust. Then, between 4 to 3.5 billion years ago, the lunar mantle underwent an acute overturn. So the bottom of the lunar mantle moved to the top. And when it did this, there was extensive lunar mantle melting. The bands that were created at that time, they kept hitting the base of the crust. And because these were hot stuff, when they hit the base of the crust, if the crust, whatever the crustal material was, it would be automatically melted. So wherever there were proctorites, they would melt to form silicic melts. Now, the crust is so thick that these melts will not be able to rise to the top and be exposed, as we see it. The only way that you can do it is if you have meteoritic impacts that will kill the crust and create fractures. And that is exactly what we see. The timing coincides with the late heavy bombardment on the moon. And as a consequence, what we created pathways for granitic or silicic magmas to rise to the surface of the moon. So we think that this is the only model that is really consistent with what we see on the moon. Now, the late heavy bombardment is a period of an intense meteoritic bombardment of the Earth-Moon system, which occurred between 4.1 to 3.8 billion years ago. And therefore, this probably was instrumental in the emplacement of these fencing massifs on the moon. Surprisingly, if you notice this time period, this is also the age of the oldest silicic rocks we have on Earth. Perhaps the same kind of mechanism could have created the nucleus of the earliest continents on Earth. We still don't know, the jury is still out on it. Now, we've created, let's say, we have a method in which even with a dry basaltic rock, we can actually create, silicic magma. The problem is to sustain granitic magmatism on planetary bodies, you actually need to have introduced a lot of water into the shallow levels of the mantle. That is an essential prerequisite. Now, on the moon, that was clearly not possible. The moon is much too dry. What about the other planets? Do we see any evidence on Mars, for example? Another planet where we've recently been able to send rovers. Do we see any evidence for that on Mars, that there was surface water there? Now, Mars itself, apart from this tasty little bit, is actually a planet. And it's this fourth planet when we move away from the Sun. So this is where it is, distance-wise. If you compare it with the Earth, it's smaller than the Earth. It is lighter than the Earth. Its surface is basalt, but it is heavily cratered. And the age of this old crust, right, is much older than the oldest crust we see on Earth. So the Martian crust is more than 4.5 billion years old. And again, like the Earth, Mars also happens to have a crustal dichotomy. It's got a heavily cratered southern highland, and you've got very smooth lying northern lowlands here. Let's see. Oops, yeah. So these are the northern lowlands, and these are the southern highlands. And you can see these are about 2 to 3 kilometers elevated above the lowlands there. Now, if we look at Mars in this context now, questions we're asking from Mars is, did it ever have water on its surface? And if it had water, was it at some time able to sustain any life on that planet? If there was, it's clearly not there now, how do we begin to look for it? I mean, how do we from Earth begin to search for that life on Mars? And then we have to think of some techniques which are signatures through which we can actually identify the evidence that we have of life on those planets. Now, to answer this very question, first of all, to find out if water was there on Mars, right? The Mars Exploration Rover program was begun by NASA. And the Opportunity rover was actually directed to land on a part of the Martian surface that had evidence of weathering, of aqueous weathering. Now, this really means that it was red. We know Mars is known as the red planet. And one of the reasons is that it's red is that it contains a lot of iron in the basalt on its surface. And most of that iron, when it's oxidized and becomes wet, it becomes like rust, and it's red in color. So this spectral signature was detected from the orbiter nations. So what they tried to do is to actually send out rovers to actually determine whether there is anything that can be interpreted in that particular manner. So Opportunity actually landed on one of the places where you had this particular signature, and where it landed is a place called the Meridianian Planet. It's actually at the boundaries between the highlands and the lowlands. Now, when it landed, astonishingly, what it found was a basaltic crust. And on top of the basalt, it actually found sedimentary rocks with cross-bearing. And this sedimentologists actually studying this began looking from the photographs. They actually said that these were all reworked evaporites, which would overlie the basaltic crust. This was named Burns Formation for a man who predicted this many years before anything landed there. And when you look at this particular region here, the Burns Formation, the sedimentology indicated that they had been transported under both subaqueous, which meant that there was water on the surface, liquid water, and also wind action together. These were responsible for actually creating these particular sedimentary rocks themselves on the Burns Formation on Mars. Now, this was what they expected to see. Right? But what they also noticed, astonishingly, is that when it landed there, apart from the hematite which they were looking for, they also found evidence of hydrosulfate mineral called jarosite. Now, this mineral jarosite, it made up almost 10% of the outcrop that you could see on the Meridianian Planet. Now, this is surprising in a way, but then after more rovers were sent to different parts, jarosite, we realized, is now present all over the Martian surface. It's quite widespread. Now, why is this such a surprise? Now, this is the formula of jarosite. So it's hydrous sulfate. Now, it is important fundamentally, first of all, because from this group here, you realize that its existence requires the presence of water. Otherwise, you can't get hydroxyl groups. Secondly, the iron that you see here is entirely ferric iron. It is not ferrous. So you must have had oxidizing conditions on the Martian surface if you wanted to create this particular molecule. And of course then, because it's sulfate here, and from experimental and thermodynamic evidence, we know that this particular mineral can only precipitate from waters that are extremely acidic. That is, the pH value is less than 3. Now, on Earth, jarosite is only very rarely associated with basalts, unlike what we see on Mars. And these low pH waters, these can only, it can really survive within acidic rocks, but in contact with very basic rocks like basalt, it would immediately be neutralized. The acidic waters would be neutralized. So then, to understand, how jarosite can exist on Mars and what it actually indicates, we need to look at an Earth analog. Is it possible that on Earth we have a similar sort of thing, where we can actually try to begin to understand the jarosite forms? Now, this is difficult because jarosite is very rare on Earth. Although it's rare, it doesn't mean it's absent. And interestingly, we do find this in one place in India, and that is in Kutch, which is, okay, probably use this. Yeah. So this area of Kutch, it's a place in Kutch called Matarmat. It's a village right? And this is on the way to there. This is a person whom many of you might know. Now, this area is within the Deccan Traps. It's part of the Deccan Traps. So you have the Deccan Traps on which the Cenozoic succession is laid, and below it you have the Jurassic. There is a stratigraphic succession. This is the Cenozoic part of the succession. It's not very important to realize what the rest of the succession is, but immediately above the Deccan Traps there is a discontinuous unit which people have called the Matterhorn Formation. And this is the one which is of interest to us. This lies immediately above the basalts. Now, the Deccan Traps themselves are made of these columns here. So you see these around the basalts, which is where fresh samples of basalt can be collected. Now, the upper part of the basalt is very weathered, and it forms these spheroids. So it's characteristically showing spheroidal weathering. So clay minerals tend to form here, and this is very typical of the rocks that you see above the basalts. And just above this, then, you find these sedimentary rocks, right? Many of which contain shear horizons where you have these cross-cutting yellow veins, and these cross-cutting yellow veins also are parallel to it. So both parallel and cross-cutting. Now, these veins are on the horizons that are just above the basalt. These veins themselves, when you analyze them spectroscopically using a variety of techniques, all confirm the existence of these hydrous sulfate mineral, and it is jarosite. So it does exist in a natural setting in India, just above the basalt, in sedimentary rocks, just above the basalt, which is remarkably similar to the situation that you see on Mars. So it's a fantastic analog in that particular way. But what is important here is that since it's cross-cutting, it's clearly not primary. So this mineral was actually formed after the rock formed. So it's something that formed afterwards, something that was created afterwards. Now, the question is, why did jarosite form in this setting under natural conditions on Mars? In Kutch, for example, at Matterhorn. Now, it was secondary in nature, so it wasn't related to sulfur emanations from the Deccan volcanism. It was not related to that, as some people initially suggested. This post-dated it. However, we know that jarosite has another property. It actually coexists with or it exists or thrives under water-limited conditions. And water-limited conditions means that the water is to rock ratio must be low. It means that it's wet, but it's not completely dry. You have a low water is to rock ratio. Under these conditions, Kutch itself, you can see that the original sedimentary rocks must have been deposited when there was a lot of water inside the rocks. But then, ultimately, Kutch today is extremely arid, so there was a change in the climate. And we think that that is really about the time when jarosites precipitated, when the amount of water was actually decreasing. So, how does this reflect on Mars? It actually tells us quite simply why jarosite is surviving on Mars. Because this was created at a time when Mars, whose surface actually had a lot of liquid water, lost that liquid water. The Martian surface dried up at some time in the past. Incidentally, this timing was also around 3.8 million years ago, coincides with the time of the late heavy bombardment. So all of these conditions seem to tie up. We have evidence now on Mars that there was liquid water, and we lost that liquid water for some reason in the past. Now, on Mars we know that we have liquid water. It had an oxidizing atmosphere. So the obvious last part of the question that we would ask is, did Mars host life at that time? You had oxygen, you had water. What if it did have some evidence of life present on it? Now, the fact is that if you want to stabilize life, water and oxygen are not enough. You need some critical elements to be present. And what are these critical elements? The elements that you need to stabilize life is obviously carbohydrates. You need carbon, you need hydrogen, you need oxygen. You need to have sulfur. Sulfur stabilizes protein structures. You also need to have a variety of any of these elements. Boron, molybdenum, germanium, vanadium. Any of these elements, if they are present, they can be vital in stabilizing the structures that you can actually see in many types of carbohydrates. Now, they don't do this in their elemental form. They only do this when they combine with oxygen as borates, molybdates, germaniates, or vanadates. And in that case, what they do is they stabilize the structure of organic molecules, particularly pentoses, 5 carbon sugars. So these structures are actually stabilized by the presence of these elements, if any of these are present. Now, knowing this, NASA sent another rover. This was Perseverance. And this was with the mission of trying to detect life on Mars. Now, the thing is, it was detecting features, trying to detect features where it can be, but it's really actually looking for a needle in a haystack. How do we make out whether it contains life or not? The only thing is a combination of spectral signatures. So what are we actually looking for? What kind of signatures do we think Perseverance should be looking for? Now this is what we are trying to detect. If we have these signatures which sustain life, what should we see? Where should we look? Now on Earth, for example, it was thought initially that the earliest forms of life, they were sustained in the vicinity of submarine hydrothermal vents. So this was actually photographed by David Attenborough first. But then from that time, people thought that this was the earliest evidence of life. Maybe that's where it originates. However, now we think that it's probably a little different. The reason is that if you continuously subject any particular parts of these nucleotides below water continuously, these will not be stabilized. So what you need are alternate wet and dry spells. So you need to have spells in which it's underwater, you have to provide water, remove the water. That dry period allows the nucleotide to stabilize. And then that can then polymerize and form ribonucleic acid, which is the essential ingredient from which life would start. So you need these alternating wet-dry cycles. Now clearly, alternating wet and dry cycles are impossible below oceans. They are continuously underwater. So the only place that you can think of where you can get alternating wet and dry cycles would have to be on the continents. So again, the first part of my talk, the continents, where it comes in. To sustain life, you need continents. But what are these potential localities on continents? Now, to stabilize life, you need some extra energy. And that is most likely wherever you have hot springs on Earth. So the heat energy of the hot springs, these can create potential habitats, even if they are extreme environments. What they do is to form, in biological terms, they form continental warm little ponds, hot water ponds. And they have alternating wet and dry cycles. So the water collects, evaporates, and then these particularly are features that are common in hot springs. And then, if near these hot springs you have those critical elements necessary for life, you can actually form life and stabilize life. So in other words, if we can identify some such hot spring on Earth, right, with this combination of factors, we know the spectra that Perseverance needs to look for in order to detect life. So, what do we need? We need an Earth analog. So we need to look for a place on Earth where there are hydrosulfate minerals, because the hydrosulfate minerals like alunite, jarosite, and gypsum, because they are formed under water-limited conditions, it means that you have to have dry and wet cycles together. Opaline silica, these are intrinsically linked to hot springs and freezes. And if you get borates, that would provide the critical missing link for stabilizing nucleotides. Now, this is important, but why boron in particular? Why not molybdenum? Why not germanium? Why not vanadium? That is because the element boron has been reported already from Mars. We know boron exists, but we don't know if that boron is in the form of borates. Why is that important? Now, boron is one of the key elements. We know what it does specifically. It controls the reactivity of prebiotic organic compounds. And these are compounds such as dextroses, heptoses, pentoses, etc. These stabilize carbohydrates as well as ribose. And of course, as I said, boron has been found in a Martian meteorite. It's also been found, reported recently, from the Gale crater, from a calcium sulfate fracture present within the Gale crater itself. Now, in India, there is one such site that has more or less these conditions, and that's the Kuba hot spring in Ladakh. So it's a beautiful area, it's a geothermal field, we know the hot springs are there, it's a tourist spot. And if you look at this place, then you actually find spectra which tells you that gypsum is present. So this is gypsum, this is opal. You can actually see this in the SEM image, and you get spectra which confirms their presence. This is the spectra of gypsum, this is the spectra of opal. And you see these fractures these are the places where they actually stabilize in Puka. You also have hydrosulfates, you find alunites, and then I think you have a jarosite also in these. So the spectra confirms the presence of wet dry cycles in Puka. So you have all the features that you actually need. And not just that, finally, You have boreates in Puga. And you actually have algal mats stabilizing in that particular environment. It's an extreme environment. You can see because not a blade of grass grows there, but you've got these algal mats which are actually capable of being stabilized in these environments themselves. So all of these features together are present in the Puga Valley. So you can actually see this in the visual vicinity of the hot springs. So why is this important then? The Puga hot springs, these are excellent terrestrial analogs. If you want to study Martian evaporites, borate mineralization on Mars, but of course if you can fully characterize the spectral signature of that locality, the geochemistry that we can interpret on the basis of spectral signatures right now from that and correspond, because we have an analog where we can test out these things. It can be invaluable for identifying extinct, maybe even extinct, hot springs on Mars. And these hot springs will be the ones which are most likely to be of astrobiological significance. Now, so let's wrap up the whole thing together. The moral of the story. For us to survive on this particular planet, a number of factors had to converge. Now, we needed to have a surface temperature that stabilized liquid water. For that, we needed to have continents to form, and we needed them to protrude above sea level. Now, we know that continents are formed of silica-rich rocks, and these can form from planets which have silicate interiors, right? And these are produced by more than 1 or 2 stages of partial melting. Now, the earliest continental nuclei, they may not have had the water to form. They could have resulted from meteoritic impacts. So it might have actually formed the nucleus from which the continents then grew. However, if you want to form larger continents, as we do on Earth, this must be because you had surface water which was carried down by processes such as plate tectonics into the shallow mantle. And when you melt the mantle under hydrous conditions, you get basalt, which is water rich and which can fractionate to give you a acidic type. Now, surface water needs to be present and to circulate into the mantle, and this circulation of liquid water from the surface into the mantle, that needs plate tectonics, and only the Earth has that among the planets we've seen and the planetary bodies we've seen. And of course, finally, you need an energy source and you need a combination of critical elements. And you need them to all get together on a continent in order for life to stabilize, in order for life to proliferate. Ultimately, then, you begin to realize that we are really lucky to be able to live on this particular planet. This is an image from the lunar reconnaissance orbiter, right? This is an image of the frontal part of the moon, and this is the Earth rising in the horizon. I think at this point, the only thing we can actually realize is we're really very, very lucky that we live on this planet. Because all those different factors, they had to come together for us to create life on this planet, for us ultimately to be hearing a lecture here in this particular theater. So, at the end of it, I would like once again to express my extreme gratitude to Professor Jean-Paul Gauche, to the Department of Geology of Presidency University for the invitation to the Geological Institute. I'm a proud member of it still. I remember Dr. Shah saying that in our very first class in the new lecture theatre, that you are here, you automatically become members of the Geological Institute. Happy to know it's still there. And the final image that I think we should leave with is this particular photograph which we excavated from our classmates a few days back. So this has Professor Gauri Shankar Kharagpur there, naming all the others. This is Abhijit Chakrabarty, my batchmates in our third year bachelor BSc field trip. This is Priyaputta Shah. This is Abhijit Banerjee. Shamir Kumar Bhattacharya was the topper of our batch. Deepan Jana is a name who Presidency University might be familiar with because he's donated a lot of equipment here, and I think he's also planning to give something more. That's what he told me a few days back. This is Joydeep Mukhopadhyay. He's also in the West Bengal government in Calcutta. Ramadev Mukhopadhyay is not in geology anymore. Arnav Bhattacharya, we've lost contact with him. Abhijit Datta, not doing geology, but he's somewhere in Africa doing corporate work. Devabrata Prime, he is still based in, he's now in Durgapur, final stages of his, just before his retirement. Prosenjit Hans is the person we were discussing a few minutes back. He's currently also based in Kolkata, but right now he's in the US. Shivabrata Bashak is in SAIL, Steel Authority of India. He's high-flying general manager of geology there. Probir Pal is a big LIC operative. Probir Panda, he was of a senior batch, but he didn't speak with us. I don't know where he is. Saibal Gupta, who was lucky enough to get a plane ticket last night to go to Hyderabad, he's a DDG of the GSI, so he managed to avoid attending this talk. Gautam Kundu, I don't know where he is, really lost complete contact with him. This year is yours truly. Two people are missing from here who were in this. One is Suhas Chaudhary, I don't know where exactly he is at this instant. He was supposed to be here, he was with us in the field trip. And of course, Bhaskar Bhattacharya. He's never there in any of our photographs, he was always our photographer. So, with this, and with a final little bit, mark of respect to this gentleman. Thank you very much.
Thank you, sir, for the thought-provoking presentation. So normally we do not offer question and answer in invited lectures, but if the speaker agrees, we can take a few questions from the audience, especially from the students.
Well, it could be anybody. Students is most welcome. And speaker does agree. When the speaker can't answer the question, he'll feel tired. So you can go ahead and ask. Students are always reluctant to ask questions. Yes? Sound us.
Thank you, sir, for this wonderful talk. Sir, you said that about 4 billion years ago, Martian maintained overturned. What is the reason behind that?
4 billion years, the lunar mantle overturned.
Lunar mantle.
Okay, it's the subject of another work that is currently in review. Right? So it's an experiment. When the whole of the moon is at some time is believed to have melted. So the lunar mantle melted. When it melted, it produced a lot of material in which there was a lot of basalt. There were cumulates formed at the bottom which form the mantle of the moon today. And at the top you had layers of amatosite and the cumulates. The part in between, that is where the last bits of melt were crystallizing. Now, for some reason, the moon contains a lot of titanium and iron. And this little melt in the middle sandwiched layer, which was just below the crust, this last bit of melt contained titanium, contained iron, and this was liquid. Now, this iron titanium liquid is extremely dense. It is denser than the material that had already crystallized. So what happens is that this density difference caused an instability because of which the whole thing overturned. When it overturns, hot material at its bottom, when you decompress, there is a phenomenon called decompression melting. That is why we get melting in the mid-ocean ridges. So really, that is the reason why there was a lunar mantle overturn.
Thank you, sir.
Anybody else?
It's a very good question, actually. Yes, please.
Yeah. I just read somewhere 2 years back there was some return samples where they discovered some granitic rocks, which I think dated close to the Castanites, 3.9, 3.8, something like that.
Well, I don't know about the dating part, but yes, you're absolutely right. The lunar return samples that I talked about, some of them actually did contain microgranites. So they were granophyres. What is most interesting is, if it's a granophyre, it must have formed at the eutectic. So you know there must have been a liquid. So we know it's there. 3.8 and 3.9 is roughly the time. In fact, most of these silicic constructs are of that age. And there is a very strong correlation with this late heavy bombardment. So that's why we think that it's connected. And if it was the case, if meteorites bombarded the moon, they must have done bombarded the Earth as well. The Earth has a much larger surface area to bombard. So, I mean, it's interesting that the oldest continental rocks we see are also roughly about that age.
Thank you, Professor Gupta. It's a wonderful talk. So just in continuation to his query, do you mean that it's a sort of mechanism like salt dome formation?
Sort of. The salt dome is that the salt is, gravitationally or density-wise, it's lower. It's a lower density than the between on top.
Yeah.
Right? That's how it goes up. It is a sort of that where it's the difference is that this is initiated by gravity instability at the bottom in the case of a salt dome.
Yeah.
In this case, the gravity instability is at the top.
But the final picture will be the same. Right?
Yeah, there won't be an overturn. There won't be an overturn. See, the whole idea of an overturn comes from lake dynamics. So it was basically the idea that things could overturn. It came from a lake in Siberia. A whole set of 3 or 4 villages died overnight due to methane poisoning. And what had happened there is that the lake overnight had overturned. So you had rotten material at the bottom where methane had accumulated. And then because of an inversion in the density, then the whole overnight it overturned and the methane was released. And because it's heavier, it just spread into the villages, and I think several villages together were suffocated. That's when the idea of this overturn, mainly in Fiji came in.
Thank you, Professor Gupta. I have just a very simple question. See, you indicate kind of dating of some event in the lunar perspective. Now, how those dating, if you compare with the dating which has been made, radiogenic dating in the Earth's crust, how they are organically connected? They are two different altogether methods. No? So, can you just say that these can be comparable in that way?
But the reason that they correlate is because of the lunar return samples. So what was done is that, what I believe was done, is that on the moon, because we had return samples, people dated them. And we knew where we had collected those samples, and they correlated this with the impact, the frequency of the craters on that particular surface. So the calibration is against radiometric dating on the moon. Now that has been extrapolated to other planets. For example, Mars, Venus, etc. So the surface ages are calibrated against what we see on the moon. We don't have return samples, obviously, from those places. And when we get them, they might, tell us that we are wrong. But for the moon, we have a much better control because we know we have a control because some samples are dated. We know it. The students are getting tired anyway, so she.
So we come to the end of the question answer session. Now I would like to call upon stage Head Department of Geology to hand over a token of gesture to the speaker to mark this occasion. To conclude the event, I would now like to call Secretary of Geological Institute, Kingshuk Pal, to deliver the vote of thanks.
Thank you, Shampana. Good evening, everyone. It's my privilege to deliver the vote of thanks on this special occasion. First and foremost, I extend my heartfelt gratitude to Professor Saibal Gupta for his inspiring and thought-provoking lecture. His talk was a remarkable blend of deep scientific insight and broad interdisciplinary relevance. We are truly honored to have had the opportunity to learn from such a distinguished scholar. A special word of thanks to our distinguished alumni, whose unwavering support, thoughtful suggestions, and generous financial contributions have played a key role in the accomplishment of the events throughout the year. I extend my sincere thanks to the Honorable Vice Chancellor and the authorities of Presidency University for their invaluable suggestions and constant support, without which conducting this program wouldn't have been possible. I would like to convey my deepest thanks to all the fellow research scholars, undergrad and postgraduate students whose active participation to conduct all these events throughout the year make the event successful. We deeply acknowledge the speakers and participants of all programs held in the last few months during our centenary celebrations. Thanks are due to all the sponsors who made us realize our dreams. I would like to convey my deepest thanks to our faculty members and departmental staff whose dedication in organizing the year-long events have been contributory to the success of the Birth Centennial celebrations of Professor A.K. Saha. I would also like to thank all the faculty members, students and guests who have joined us today in offline as well as in online and contributed in making this session engaging and meaningful with their presence and thoughtful questions. Lastly, thank you all once again for being a part of this enriching experience. We look forward to carry this spirit and keep the ideas of Professor Saha alive. Thank you all. I would now like to request all to proceed for a cup of tea outside the hall.